So in this case, we were talking in tank approach actually that you are feeding something to a particular reactor or vessel. It could be anything actually, not it can be a mixer, it could be a means anything. So what you are feeding something, so you may feed one of the component, maybe one stream this side, or you can feed multiple streams also. You can have more than one stream, maybe from this end, maybe from somewhere here, maybe from somewhere here, right? So there could be several component which may come in, right? Hello, can anyone hear?
Yes, sir.
Yes, sir.
Yes, so
So there could be several stream which might be coming to this particular tank or the reactor. And what is happening in tank approach is the leaving stream, whatever will leave from here, would have the same properties what are there inside this entire tank actually. Okay. So here we were talking, let's say, uh, some A is getting feeded, and after it might be happening some reaction inside. So you are getting some A, some B, or maybe some other component also. So that depend what process is taking place inside the reactor. So and then this part is the leaving. So for that only we wrote actually for the mass balance parts, because mass balance is just this one, that mass accumulated would be equal to mass in minus mass out, right? So and you cannot have here a mass generation term because mass cannot be generated also, right? So mass cannot be generated. So whatever mass is accumulated is just in minus out. So therefore mass generation term is not there. So then so you might be wondering that in case of the reaction that may happen. So in for the reaction part, if you are putting a generation term here, so but even though that mass will not change actually, because mass is a conserved quantity, right? So so in that case you can write in case of the element part actually. So if you are writing same equation in terms of elements, you will not have the generation part. If you are writing for component or compound, you may have some generation term here also, right? So in this case, mass is nothing but you have calculated density into volume. So this much is inside this tank, and you have just calculated for a differential time. And once you will take, you will put the limit here at this particular time. Actually, this your delta t tends to 0. So so if this you will see that your delta t tends to 0 part, then in that case you will end up with the this bottom equation actually, and you can write this one in terms of derivative. And once you have in the derivative form, now it is up to you whether you want to apply for the steady state or unsteady state. If you want to apply for a steady state, this is currently for without the reaction part. So you don't have here the some K1, C1 terms here. So a steady state, this time derivative will go away. So you will have only this term, only the right hand side part, right? So if you want to write individual component, so you just change density by a concentration of individual component. So same thing can also be the written for in terms of energy also, right? If you want to write in terms of energy, and energy cannot be the written in terms of individual component. Energy is always the written as a whole actually. So don't get confused that energy you can write individual component and all this. No, it's not. Energy is a combined uh, effect of the entire process. So you can write energy in that particular form. So this is what we have covered in the last class. So this is the tank approach. Next approach is actually your tubular approach or something. So in case of tubular means, let's say you can take maybe a cylinder something. So cylinder or a reactor. So let's say we are taking this one. So let's say you have a this much big actually a reactor or a tubular reactor or maybe a pipe something. Now what will happen here if you are feeding something to one of the ant, maybe you are feeding, let's say you are feeding from here. Let's say you are feeding from at this particular ant here. Now what will happen here? So if you are not making bell mix conditions inside this particular entire reactor somewhere, so what will happen? Your things would change along the length. Yes or no? Hello?
Yes, sir.
Yes, sir.
So in that case, but you have to apply your this again your balances. So to apply the balance, you have to choose the segments. So let's say you are choosing some segment somewhere in the middle somewhere. Let's say you want to apply somewhere here actually. So this segment, let's say you have chosen a differential length or let's say a small volume of that one. So in that particular part, you want to apply the balance. So you can consider that this particular this region actually in this you want to apply. So this might be considered as a again a tank approach. So you might be putting maybe I can make a different figure here, maybe or this way. So let's say you are putting a different tank here. So let's say you have taken one differential volume here. You can take maybe another one, maybe at some other point, or maybe another one at some other point. So you are actually taking several tanks along the entire, you can say, the entire volume of this particular tubular, the mean the reactor. So you can write same equation for the, let's say this volume, same equation maybe this volume, same equation maybe this volume. But what will happen in this particular case that whatever is there inside this could be treated as one of the tank actually. So inside this there is no variation, but however if you will reach to this particular segment here, there the variation here. So so you can take this volume as low as possible to convert to actually capture the entire behavior in this entire length. So in this case, you can say your parameters means parameter could be your concentration, could be your temperature, could be your density, and these may vary along the length. So this is your length coordinate here. So if you want to say that, so let's say this one is your length. So in this case, as you will move to this side, so your length would actually, your parameter will change with respect to your this length coordinate here. Fine. Hello.
Yes, sir.
So this could change along the length. And what are the parameters you have? You have your, you could have your density, concentration, temperature. These are the main parameters you have all the time. No matter what process is taking place inside this particular equipment, but these are the only parameters you have there. Now, this particular process could be steady or unsteady actually, so that you don't know what will happen here. So in this case, if this is a steady part, so what will happen? The steady case also your things would change with respect to length, not with respect to, hello,
Yes, sir.
can you complete my sentence?
Sir, time.
Yeah, so in case of steady state operations, your parameter cannot change. Let's say you are talking about at this particular x coordinate, let's say this value is x1 here. So if you are talking about steady state operation, your things would not change at this particular coordinate. If you will move to this coordinate, again your things would change. However, things are steady state. So you can say your parameters are the space functions, not the time functions in case of steady state operation, right? And then if you want to cover this entire thing, so you can take infinite the number of this start and the means approaches, and finally you will end up to the your tubular approach actually. So it will come means that thing might have taught to you also in your the CRE, that your plug flow reactor or tubular the reactor can be replaced by infinite number of CSTRs, correct? Hello?
Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
So can you write something for this? You can write the heading a tubular approach and write the something for this. Do you want to write or whatever I have explained is fine?
Sir, it is fine.
So no need to write. It's okay then. So that's fine then. Then one more approach is called a lumped approach. So can you differentiate between a lumped approach and tubular approach? When do you say a lumped system? Anyone wants to say something? Hello? What is a lumped parameter approach? Can anyone say something for this?
Some sir lump parameter means it is the average. We can assume an average value of some quantity,
Uh,
Sir,
or we
we
can
okay.
sir,
say
sir,
major
we can
part.
neglect the thermal resistance.
Thermal?
Resistance.
What
Sir,
happened to
like
that?
sir, like thermal in the reactor, there is a due to heat thermal expansion may take place, so we can neglect that.
Okay, so lumped means actually you are just lumped it again. You can say a different way to handle this. Your tank approach means again. So again, you are talking that you are only interested in the final changes actually. You are not interested what is happening in between. Just like that, you are heating, let's say, just like a boiling something is potato in water. So what you are interested in that, you are not interested what would be the surface temperature of this potato and how this vary along this entire bulk of that particular thing. So you are just interested what is the final change, just like a tank approach part, right? So that is the lump parameter system means you are talking about the overall change means just like if you will insert, let's say you are taking this body, you have one body here, and let's say you have another body, this one. Okay. Now, this either you are heating or cooling these two bodies. Means let's say you are heating the first one. So you are not interested what is the variation this along this radius inside this entire bulk of the means the material. You are only interested what is its temperature. As this Bhanu said that you are interested only in the means some sort of the average temperatures or mean property. Correct? So this bit only comes that once you have a very well mixed means approach means otherwise let's say you have a very high temperature at this of the surface if you are heating it and at the center you will have very low temperature. So also obviously your variation would be too high if you are heating it, right? Yes or no? Because it will not reach that much faster at this particular place. But in case of lumped means approach, you are considering that there is no variation in this entire spatial coordinate. Means either you move to at r equal to 0 or r equal to capital R. There are no variation here in the properties. So this could only be possible when the things is well mixed. So well mixed could be possible if you have a liquid system which is well agitated, or in case of solid, it can also be possible. Let's say if your heat capacity is excessively high, so what will happen there, that as soon as your temperature or the means the energy will reach to the surface, it will immediately transfer to the entire material. Okay, that can also be possible in that particular way. So if it is bad conductor of heats, in case of energy transfer, it cannot be treated as the lump parameter system, because you will end up with some very wrong model, and finally your material may be burned out actually, because at one of the end your temperature is very high, is at one of the points your temperature would be very low, and you are considering as a lump parameter system, so that will not serve the purpose. So lump parameter approach you can consider most of the time in case of well mixed liquid systems, or maybe a well mixed the solid systems, not a solid material, where the governing property have a very low value. Are you getting it? Hello?
Yes, sir.
So, and another one is the distributed parameter one. So distributed, again, you will go to the your tabular approach. Here things are the space coordinate. So you have the space and time. So these are the different means that you should not confuse between what is lump, what is tank, what is tubular, and what is distributed system actually. Distributed means you are talking about the variation with respect to time and your space coordinate. Lump means you are not considering any variation, you are just considering a homogeneous system, right? Now we want to develop develop a mathematical formulation or mathematical model. So how do we go about? Can anyone tell in the short actually what we have talked so far? How to go about in model with the development? Anyone can say something?
Sir, we'll apply the material balance here. Then we'll derive the design equations then.
Right.
Input plus output, input minus output plus generation is
You
equal
want to
to
say the
accumulation.
material balance one, correct? Correct or no? Material balance is one.
Yes, sir.
After
And
that,
energy balance maybe, if
energy
possible.
balance is okay. Yeah, it's always possible actually. So there are 5 steps, as you say, the material balance. You want to say that in all material balances, what you have started in the beginning. How do you start the material balance?
We add the input, what is being fed to the reactor.
Okay, maybe something you will take something like that. For what you want to do the balance, some basis, some quantity, or you want to process, right? Hello,
Yes, sir.
right? So you want to say some basis or some quantity, some capacity for which you want to do your entire exercise, right? Maybe that is your choice, or maybe depending on the need of the process. After that, basis, You have taken some bases. Then basis के बाद क्या करेंगे?
Sir, we make a block diagram and in that we make a control volume.
Yes, so you will draw that, you will apply your fundamental principles, right? Your physical and chemical laws, right? Correct or not? You will apply your mass balance, you will apply your energy balance, you will apply your momentum
Yes.
conservations. Correct or not?
Yes, sir.
You will apply all your fundamental principles, mass, momentum, energy, entropy, and your chemical potentials. So all fundamental laws now can be applied because you have now considered a basis and process, you already know something. So you have everything. Then after that, you have applied mass balance, energy balance, entropy balance, momentum balance, chemical potential, equilibrium part, right? You have means applied all of them. Now what is next? Hello?
Sir,
Second part,
boundary conditions.
हाँ बोलिए बोलिए.
Sir, boundary conditions
Yeah,
or method to
boundary,
solve.
yes, yeah, boundary is fine. So for to define the boundary again, I think you will start again something because after applying your these all fundamental laws, because those fundamentals cover everything, all possible things, maybe 2D, maybe 3D, maybe 1D. So you always write all the time your 3D, always all the time, all variation with the space and time. So you will consider everything in your all fundamental laws, right, in the beginning. Now, this may not be true for your process. So you have to simplify your equations or your fundamental laws depending on your process needs. So you will always consider some assumption, right?
Yes, sir.
Because without this assumption, you will not be any means the assumptions makes your formulations or solution easier. That the two purpose. If you will just means assume too much, you will end up with a wrong model. If you will not assume anything, you will just consider everything in the theoretical point of view. In that case, you will end up with the complicated things from where you will not move anywhere. You will stuck at one of the point because there are so many variables, so many parameters, and in some most of the time you may not be in the condition to solve it. So to simplify it, to get the realistic one, you just consider some realistic assumptions there, right? So realistic assumptions with the simplify close to a practical values, and that comes based on the practice. It's not like that you can then neglect anything. No, it's not like that. Just like a PFR thing, if you are talking about plug flow, the reactor, and let's say the radius of the reactor is not very large, so most of the time you just consider there no variation along the radial direction, correct? Hello?
Yes, sir.
Yeah, a radial direction as far as you are talking about the concentration part. Let's say you are talking about the heat transfer part. So heat transfer, let's say energy transferred from your the material to the body of that. There would be most of the heat transfer would be in the radial side because you have the material there, you have metal component as compared to the axial side, because the axial side is the fluid, the element, fluid are the bad conductor of the heat or the something. So there would be less conductivity in the axial side as compared to the radial side. So you have to, these assumptions will make your model to close to the realistic, and it will simplify your basic fundamental equation which you have applied. Correct?
Yes, sir.
Next part, you want to, once you have assumption part, you want to have a, this is called a mathematical consistency, or you can say mathematical consistency is what you will do here. You will do here your degree of freedom analysis part, and to make sure that from there you would start your calculation part actually, right? Assumption may, once you have put your assumptions, you will get your boundary condition. Everything would come there in that particular part. After that, you need a mathematical consistency part there, that you have to make your degree of freedom analysis there, so that every segment would have a degree of freedom should be equal to 0 in order to get the unique solution. If you have degree of freedom is more than that, it means you are getting multiple solutions and you may not be sure what is happening actually. Correct? Hello?
Yes, sir.
After that, once you have this degree of the freedom analysis, you have all boundary, you have your assumptions, everything. Now you want to solve it, right? Hello? Somebody should respond. If otherwise, who are not responding, let them make them absent only. Okay, what is this? Now, solution techniques. Once you have a model, you have a degree of freedom, everything has been done. Now you want to solve it. Can you take the any one of the technique to solve it? Hello?
No, sir, we take only that which fits the data.
No, it's not. There are so many techniques which can fix the data. Data to ironing. There no data has come so far. In model development, if you are talking about model development by first principle, you don't have any data. If you are developing the model by first principle, a mathematical model, you don't have any data. Data comes in case of empirical modeling or validation of the data. So here you are talking anything in terms of variables only, and you don't have any, not even a single value. You are just solving your equation in terms of variables, that's all. So data are not there at present. So,
Sir, sir, then we take from the previous studies. Model.
previous?
So model from the previous studies, the equations from the previous
No, we
studies.
are developing the model. So we don't have anything actually. I am just talking about solution technique. Can all solution technique be applied, or how do we choose that which technique need to be applied? This we have talked about it. We are just compiling here only.
So we can compare the results of analytical and numerical approaches.
Yes, so you have to see that based on your modern equations and boundary conditions, you have to see whether those equations can easily would solve by analytical technique. If they can solve, okay, go ahead with analytical one only. No need to go for numerical, because numerical will give the approximate answer. So if things can be solved analytically in very easier manner, go ahead with that. If not, things looks tedious, then okay, you have to go for numerical technique. Those are called approximate the solutions. Now in numerical techniques, there are several techniques in between, so you cannot use all of them because some of them have a high amount of error, some may need very lot of computational time. So you have to, based on your own practice, you have to choose the right techniques which is easy to handle, less computational time. So in that case, you will choose a technique. Fine. Now, Sometime you might have seen that the several books, they have developed some equations or something. They talk so many things. At the end, there no equation, no solution. Will that type of model help? Hello?
No, sir.
No. So the right answer is no. You cannot, there is no usefulness of any mathematical equations or boundaries which cannot be solved. So once you are developing a model, you should always give a solution technique. If you are not giving that, applicability of that model is nowhere, it is just a waste thing actually. So this is always thing, whatever is model is developing without solution technique, or first you should have a solution technique, then you think about efficient technique which can save the time and money. So that's called a model, because you have a technique to solve it. So it can be applied. Now you have to solve it. Now you have come to here, it need to be validated. You have developed a model, you have solved it mathematically, but it need to be validated. So it need to be validated, and now it needs some data to validate it actually. So for that, most of the time people perform a basic experiment. So that's called here is verification part. Verification, or you can say validation. So the next part is this. So in that case, whatever you have solved, develop a technique. Now you want to validate that what predictions are by this particular model, are they in line with some experimental data or not? Okay. So in that case, best way that just to verify with the experiment, that's one thing. Second part is that let's say you have developed a model which is you can say the simplified the model of previous the models. You might have read your book so far, so many things. You might have seen so many models have so many parameters, something. Now you might have thought also, I can make a simplified one. I may club the 2-3 parameters, maybe one, because this is also the means another property, which can club these properties. You may end up with a different the model, but you are also solving for the same problem. So in that case, your solution, whatever is coming from your solution technique, the result must be same what previous people has solved. Correct or not?
Yes, sir.
Right, so you can make a completely new model. So if you have a completely new model, you have to perform the practical. Practical need to be a simplified practical. Don't perform a sophisticated practical just to validate any model. No, it's not allowed, because in sophistication and all this, you will always have some chances of error. Something. Easiest possible way which can be measured very easily, very confidently, that this is 100% correct. Just like that, if you are making a model, something pipe flow or flow of the fluid, easiest possible thing which you can measure in a flow is a flow rate. Correct or not? Hello?
Yes, sir.
In case of flowing thing, easiest possible thing is just a flow rate. You collect the flow rate in some week or something, or some the measuring flour, that is the easiest one, 100% correct. Chances of the error are very low. At the same time, if you say no, I will validate with the stress, shear stress variation. You know how the shear stress would be calculated inside the pipe. It's the most complicated exercise, and there is chances of the errors are very high. So if you want to validate your model with that, you will always end up with the wrong validation actually. I'm not saying the technique would fail, but it is not a first parameter which can be measured directly with more confidence. So easiest possible one is the flow rate. Next one is that you can have a pressure tappings. You can put a pressure gauge at that different point. Maybe you can have that one. Other one could be you can use your pitot tube and measure the velocity at a particular point. You can add a velocity profile. and you can validate your velocity profile by model and experiment. Correct or not? So validation is always being done by easiest possible the measurements, so that your chances of the error in the experimental data should be as low as possible. Correct?
Yes, sir.
So these are the things need to be followed in case of model that mean the development. So last the several classes we were only talking some introduction that how to proceed, what to do again. Today again we have compiled that how to proceed it, and then we will apply our all these fundamental laws. So we will talk them one by one. So let me take your attendance first.